Welcome to today's session. We're having a look at Cartesian graphing today. It's just the session's designed so that we're going to talk about a particular type of usage for the handset. Today it's Cartesian graphing. Essentially, we're going to be dealing with polynomials. Okay, but if you do have any questions as we go through, please feel free to ask. That is not a problem. Uh, my name is Simon. I'm Casio's principal trainer. I've been working with them for about 10 years now, training teachers and creating resources so that teachers are better able to use the handset. But I did used to teach. I was a head of department teaching maths and further maths. So I do have a teaching background. So I'm not just a Casio, shall we say, salesman, as it were. I approach everything that I do from a teaching and learning background. Okay. So just to describe a little bit about Casio, we are here to help support teachers and students so that basically we can all become better mathematicians. We offer training sessions for the CG50, so we've got an induction session where we do basic navigation and describe how to solve things numerically and graphically. There are emulators available. We offer student training sessions. We had one on Monday, so that students, if you're using them, they can log in and have a look at those so they become more fluent with using it. We've got revision webinars for students as well that will start again in the spring, and I'll talk more about those later on. We've got loan sets available if you've had some training so that you can get your students to use the handsets. We've got familiarization webinars that are available online. We did a series of those for the new ClassWiz handsets. Obviously, we've got deep dives, which is what this is. We're going to do a few more of those this year on different subjects, and we are just about to launch an on-demand CPD program so that you can have a go at training yourself how to use the handset. Today, what we're going to do is look at Cartesian graphing, but if I could just ask you to begin with, can you just have a look at the poll and enter your experience with using the CG50, whether you're a complete novice or you use it regularly and you're just here to see how you could improve the use, or whether you regard yourself as an expert. Okay, thanks. So most of you are novice. Okay, a few of you regular, no experts. Okay, so that's fine. So that will help me sort of guide you through today's session then. I can't assume that you know how to navigate or use certain keys, so I might explain a little bit more than necessary. Okay. So benefits of using graphing calculator. Well, personally, I think it's an amazing piece of technology, both for teaching and learning. Students probably regard it as something to just get the answers for in exams. However, it does allow them to, shall we say, investigate on their own and come up with different theories and conclusions. It allows quick switching between different representations, so perhaps algebraic and graphical, if they're talking about solving equations. They can pursue their own ideas, obviously, especially when dealing with circles, for example. Circles and intersections with straight lines, that's a good way that you can get them to think ever so slightly differently about the problem. And obviously, it allows sort of a more open style of teaching, so you can get different students looking at different aspects of things and then come together and have a nice discussion about, whether things work, whether they are equally valid, and things like that. So when we look at Cartesian graphing today, possible problems that students may come across, what we have got is the links that can be made between algebra and functions. Okay, sometimes that is a bit of a problem, factorized form and what that looks like and what that actually means. Analysis of functions. So if you're trying to solve an equation or find intersections, something like that, what's the interpretation that you can have graphically? We're going to look at transformations today of functions. So what that means, the obvious mistake that students may make is horizontal translations, whether it is plus or minus the A in which direction it goes, left or right, for example. And of course, how to interpret questions that are couched in terms of, say, transformations, which are hopefully I've got an example for you that you can have a look at later. So we're going to start off with how do students visualize functions. So we're going to keep things very simple today. I know you may be disappointed that I'm not going to draw really complicated things, but in terms of just presenting what the calculator is capable of, I am going to try and keep it simple by just dealing with a quadratic in this case. Calculator is more than capable of drawing all sorts of different functions, and you can apply the same principles to those throughout. So if we have a quadratic like this and the student is asked to draw, one of the things they might be tempted to do is use a table function, for example, to evaluate different values of the function between certain values, -5 to 5, something like that. Okay. What you can do then is access table mode. So that is main menu screen. And then you can see that table has got the shortcut 7 on the icon. You can use the shortcuts as opposed to scrolling. It's a lot faster. You can just go to 7 and you've got table mode. You need to enter a function, obviously, so that would be x squared. The default variable key is x theta t, 2 keys above 7. Okay, always use that for your variables. Square it, subtract 2x and subtract 3, and confirm with execute. Okay. Then you can populate the table with set. Default, it goes from 1 to 5, but if you want to enter, say, negative values, you can do -5. Now, negative is to the left of execute. -5 and confirm. Going up in integers is perfectly okay. So I can exit from there and then go to table, and that will populate a table for me. And that should help students with the idea of drawing a quadratic. But questions that you could ask is what sort of shape would students expect? If they've not seen a quadratic before, thought about sketching it, obviously you can get into a discussion of, what general shape will it have? You can scroll through the values, obviously, in your table, and you notice a couple of zeros there, perhaps, just because it's a nice quadratic. So you can then say, okay, what does the value of 0 mean? If they were going to sketch the quadratic, though, what would you expect them to label? Are they just going to draw a curve? Are they going to draw some axes? Are they going to do any labeling? So that gives you the opportunity to sort of promote, shall we say, accuracy for your students. To interpret a sketch, they will need some labels, and what are the important labels? And of course, is a sketch preferable to a plot? What is the difference between them? The accuracy, is a plot necessary, for example? What would happen if you did plot those points? Would you end up with a curve? Would it be acceptable to have straight lines between these points? Things like that. So you can ask your students to sketch a function, or you can use the calculator quite nicely. So sticking with the quadratic, you need to go to graph mode. So that would be menu, and then graph has got the shortcut 5. You get to the graph mode, so the function editor list, and you'll notice that the functions have been carried forward between both graph mode and table mode, so you don't have to re-enter. Okay, so it's already there, and if you choose draw, that's F6, you will get your default view for the handset. Okay, now I've reset my handset, so this is the default view. If you haven't reset, you may be getting something slightly different. Okay, but as it is, we'll assume that you have reset. This is the default view. You get a certain amount of information, and you may just about be able to squeeze the y-intercept out of that. Um, but you can scroll, so you can move the graph manually. Okay. So you can scroll down and say, oh, look, now I've got two x-intercepts, a y-intercept, and I can also see the vertex as well. So that's a pretty complete curve for you, so you can start having a discussion about it. But some of the things that are more useful when you are drawing things, I'll show you as you go along. So we've got a couple of shortcuts, add and subtract. Add zooms in. Okay, and subtract will zoom out, and you can press it more than once if you like. So, for example, you can zoom out, maybe more useful perhaps if you're dealing with, say, a cubic. So that may not be all immediately apparently on the axes, so you may not have two stationary points or even three roots, so you could zoom out to locate it and then possibly move the graph around or even change the scales so you get a better looking curve. So you've got a general shape for the curve, but what we're going to do is we are going to try and, shall we say, optimize the presentation of our function. So whenever you draw something, it's always a good idea, shall we say, to try and get the best scale so that the curve looks as good as it can. Now, I've chosen these settings just for this training session. You don't have to stick to these for every function. It's all relevant to this particular quadratic. If you want to change the scale settings, that's called changing the view window. Now, to do that, we need to press the yellow Shift key and then the V-Win key, view window, that's F3. We've got some scales there, and I'd like to change them. So we've got X-min, X-max, so that's horizontal scale, Y-min, Y-max, vertical scale. If you have a quick go at just changing those to go from -5 to 7.6, so enter the value and then confirm with execute. I'll stick with a scale of 1, and then if I change the Y values to go from -6 to 16, but now I'd like a scale of 2. Okay, so if you've managed to enter those, next thing you can do is have a go at drawing the graph. So if you exit back to the function editor and then choose draw again, you get a curve, nice shape, filling the screen quite nicely, but with room for some labels. Okay, so this then enables you to ask questions along the lines of to your students, obviously, why does the graph have this shape? You know, why is it faintly U-shaped or V-shaped if they want to call it V-shaped? How and why would this be symmetrical? Is that linked to the fact that you are squaring something, of course? Why does it have a minimum? Okay. Why do the points where it's crossing the x-axis and the y-axis, why are they those particular values? So it allows you to ask all sorts of nice questions about the particular shape of the function. And we are going to have a look at that later on. But one of the things that might be useful if you have graphed a function is you can evaluate points on it. Simply, you can do this with Shift and Trace. That's F1. Okay. Now, Shift and Trace, that will place a cursor at the center of the screen on your function. You can see it has placed it at the value of x equals 1.3. Okay. You can scroll using your scroll pad, and you'll see that the cursor moves along the function. So you can scroll left or right. Currently, because we've got these particular settings, the amount that you scroll with each scroll key press is a tenth. Okay. But what if you wanted something slightly more accurate than that or a different value? Well, quite easily you can just enter a value such as 2.45. You can enter particular values and then execute, and the cursor will scroll directly to that point with both the X and the Y value shown. Notice that the coordinates are actually truncated, but the full decimal values are given at the bottom of the screen. Okay. Um, and then you can extend that by saying, okay, if we have our curve and we are tracing points, so we're evaluating particular points, how useful is it that you can evaluate at any point? So any degree of accuracy that you like, that's quite useful, I think, personally, especially when you are asked to evaluate either functions or their transformations. Can you evaluate all points? To a certain degree, yes, because you can enter, shall we say, quite detailed decimal values or even exact values such as pi or root 2, something like that. You could enter those if needed. And that's quite nice because, for example, if you have a quadratic with a root of root 2 and you trace that particular point, you can enter it and it will show you that it is in fact 0. If you want to do further analysis of the points, what you can do is you can find the roots if you want. So to do that, that would be the yellow shift key and G-solve, which is F5. You can do all sorts of analysis here, you know, roots, local max or mins, y-intercepts, intersections, and there are further options available. If you choose root, what you'll get is that the cursor toggles to the leftmost root, and it's displaying the value of x at the bottom of the screen. That's the full value. And you can also scroll to the right as well to find the second root. So we've got -1 and 3 for our two roots. Okay. You could also make the link between roots and the intersections of your quadratic and the line y equals 0. Quite easy to do. You can just exit and then add a y equals 0 to y2. And then when you draw, you do further analysis with Shift and G-solve and choose intersection. Okay, so here we have x equals -1 for the left and x equals 3 for the right intersection. So that's quite nice, making the link between intersections of functions and, for example, solutions of equations. Doing that graphically. You could also approach this numerically, of course. You could use the equation solver to solve the polynomial, or you can use a numerical solver in run matrix. That's menu and 1. Solven, really powerful. If you had the training from us, we talk about that quite a lot. Very good at solving equations, all sorts of different equations. To access it, you use Option and then Calc, which gives you solve n. You can enter your equation, so I can enter x squared subtract 2x subtract, get it right, 3. I can make sure to use x theta t for your variable. You enter your equal sign with a shift and a decimal point. You can see the equal sign is labeling the decimal point. Set it equal to 0. And then when you execute, you get a warning that says more solutions may exist. And this is because it is actually a numerical method. Sometimes they fail. So that's why it's always a good idea to sketch as well. Exit, and it gives you the solution set of the two x values. Okay. You can, of course, as well, because we have sketched the function already, instead of using the actual function, you can use graph notation. My graph is y1, my quadratic, and you can solve that and get the same value. So that's quite nice as well. So you make the link between the graph and the algebraic method, shall we say. So then you ask questions along the lines of how are the root values linked to the function, and what does -1 and 3 actually mean to our function, which is a link to factorization, perhaps. You can also extend this and say, okay, if we have our graph, so let's do menu 5 again. Let's get rid of our horizontal line, and if I draw it, there is my graph. Can I analyze it? Yes, I can. I can shift and G-solve and then find the minimum. Okay, so quite useful, for example, if you are dealing with, in this case, polynomials or even trig functions, something like that. So we've got x equals 1, which is 2 away from our left root of -1 and also 2 away from the right root of 3. Okay. You could also, if you wanted to, you could approach it numerically and then say, okay, one of the ways of doing this would be, let's edit solve n. You can find out when the derivative of your function is equal to 0. So apply a little bit of calculus. You can use the option key in calc again to get to the first derivative. You could enter your function, or you could enter y1, graph notation, doesn't matter. You would be differentiating at the general point x, and you would want to say when is that equal to 0. And when you confirm, you get the value of 1. So you find out that the vertex is at x equals 1, and then you sub the value of 1 back in to get the y value. Okay. Of course, you could always apply this to the graphical method. So you could say, okay, here is my function. I am now going to differentiate. Let's differentiate y1. So I don't need to put the function in, but I'm differentiating at the general point x. I then sketch it. And this is quite nice, for example, if you're dealing with a bit of mechanics, perhaps. So you've got function, first derivative, second derivative. You could apply that to, say, position, velocity, and acceleration. You can see that what we have is our differential does have a value of y equals 0. So you can shift, G-solve, and root. You have sketched 2 different functions. You need to decide which one to analyze. So at the moment, the quadratic is flashing. If I scroll down, the linear flashes. I select it, and it finds out when y is equal to 0. Okay. So that's another way of finding out where the vertex could happen. And then that allows you to ask questions along the lines of how are those particular values, so 1 and -4, linked to the function, as a sort of way of getting students to think about completed square format, perhaps. Making the links to algebra, we can have a go at finding factors for our function. So we could exit. So for example, we can then delete, and we can enter our factorized form. So x add 1, x subtract 3. Okay, so you can enter a factorized form. And of course, if students are dealing with factorization, perhaps struggling with it a little bit, this might be useful, because if you now sketch, So choosing draw, what you would get is some coincident graphs, and then that offers the opportunity to ask questions such as, what does that mean? Okay, obviously it means that the correct factorization has occurred. But what if you get something along the lines of this? Obviously, that is not a correct factorization. Potentially what has happened there is that if we exit, you can see that the red graph is not coincident with our correct function. So perhaps what has happened is that they've fallen into the trap of, well, if the roots are -1 and +3, they have entered those as the factors. And as you can see, if you enter those factors, you get the incorrect graph. Okay, so then that enables you to approach misconceptions about the link between factors and roots. You can also have a look at a different form for, in this case, our quadratic. I know I'm sticking to quadratics, but this does give me the opportunity to demonstrate that you can enter all of these different forms. So let's get rid of our quadratic factored version. And then I can enter my completed square format. So we know that it would be x subtract 1. We can then square that and subtract the vertical translation. Okay, so this gives students a very good opportunity to try to complete the square on a particular quadratic, enter what they think may be the correct value, and then if they have a go at sketching, if they get coincident curves, they know that they are correct. But also, if they have analyzed the function beforehand, perhaps found the coordinates of the vertex, this then says, is there a link between completed square format and the coordinate values of the vertex? Okay, so again, helping them to understand the mechanics behind going from standard form, so we say rectangular form of the quadratic, to completed square form. Okay. And just to remind you that it is very easy to switch between all of these different forms. You can have intersections between the function and the axes, for example, or intersection between function and another function, as we saw y = 0, perhaps. You've got the coordinates displayed for all of your relevant points, so the roots and the factors. You've got the coordinates displayed for your vertex and the completed square format. So all of those make it very nice that you can link in this case, quadratic to its various forms, and make it easy to switch between all of them. If we then have a look at transformations now, okay. You are able to do direct transformations, which is very useful. And this is a topic that can really confuse students, shall we say. So if we just delete, I'm going to add an x squared, just so that we can have a discussion about, if you start with x squared, how do we turn it into our quadratic? X squared subtract 2x subtract 3, for example. So here is x squared, my next function y3. What I'm going to do is I'm going to enter that as a transformation of y2. So I need to scroll to the right there. If you do that, you can see you've got the y available for your function. So that's y2, and I'm going to do y2 to, in this case, x subtract 1. Okay, so that is not y2 times multiplied by x subtract 1. That is y2 of x subtract 1. That's why it's worth thinking of the functions y1, y2, y3 in terms of, say, f of x, g of x, h of x, and so on. Okay. So now I'm going to do y2 of x subtract 1. You could ask questions of your students such as what would they expect when you do y2 and x subtract 1 in parentheses. Is it a multiplication? Is it an of? Okay, in what way would that change x squared? Okay, if you draw, you would get 3 graphs. This gives you the opportunity perhaps to ask questions of your students, what has happened? So you've got the blue original quadratic, the red x squared, and what has happened to the green function. Is it the same shape? Has it got any relation to the other curves? Well, it's got some sort of relation to the red curve. But then you can ask questions such as what relationship? You can do further transformations as well if you like. So you can do AF of x, f of AX, negative f of x, f of negative x, f of x subtract a, and f of x plus a. You can do all the transformations that you would expect to be able to do. So if I just add another function here, so scroll right with the y. Now I want to do this to function y3. So I've already, as we know, translated for y3. I am now going to translate again. So what I'm doing here, this is a vertical translation. I can then draw, and you can see that you actually get coincident graphs between the blue one, the original quadratic, and our, shall we call it magenta, where we have done 2 translations. So then again, this is a nice way into asking students if they are coincident, that means they're the same. So what has actually happened? If you are doing a horizontal translation and then a vertical translation, the link between completely square format and the original. So that's quite nice. You can also do indirect transformations. Okay. So I'm now going to show you how you can store values as variables. So menu 1 takes you to run matrix. I'm just going to delete all of that. You don't need to. But you can store the value of 2, for example, using the store arrow just above A as the variable A if you want. Okay. So 2 is now assigned to a variable A. If we then go back to function editor in graph mode, I'm just going to delete those direct transformations. Okay. The reason I'm doing that is just so that everything is on the top of the screen. The number of functions you can actually draw does go up to y20. So you can draw 20 functions, but saving me scrolling all the time, I'm just going to deal with what you can see on the default screen. So here I can enter x subtract a. If you want to enter variables, you do need to press alpha first. You can see you get a little red A at the top of the screen, and the letter A is labeling x theta t. Close the parentheses and then square. So what sort of transformation is this? Well, indirectly, this is an f of x subtract a. Okay. Confirm that. And then when you draw this time, this may help students to think, okay, if I started off with a red x squared curve, now I've got x subtract a and a is 2, so this is an x subtract 2 all squared function. It looks suspiciously like there has been a horizontal translation, by how much. Okay, so this is really useful for getting students to think about what's happening when you're doing an x subtract a transformation. and which way essentially the graph does travel. They can do their own investigation, come up with their own conclusions. Notice the green curve still nowhere near the blue curve, so there are further transformations that need to happen. But again, it should, depending upon how it's been approached, it should help students to understand. Okay. If we look at variables next, okay, so variables, you can use indirect values if you want. So again, we're going to go to the green function. I don't need to delete, I can actually just over type. So here's x squared, subtract ax, subtract 3. Okay. So then this gives you the opportunity, okay, what do you think the coefficient of x is doing in my function? You could, of course, have had x squared subtract 2x subtract a, and then say, what is the constant at the end doing? Or you could have even had the coefficient of x squared as a variable. Okay, it gives you a nice opportunity to investigate what changing these coefficients or constants does to a function. Students may not be able to initially respond with that, but if they have the calculator, of course, they can do their own investigation. So if we then go to run matrix, and I'll just edit this one, you don't need to input it again. I'm going to store 1 as the value of a this time. And if I go back to graph mode and then draw, what you can see is if you do change the coefficient of x, it does change the shape and position of the curve. Okay, and then that might lead you to further investigation. Potentially, you might ask questions such as, what do you think is happening to the curve? This might be better supported if you draw more than one curve. You can easily do this, for example, by drawing the function with the variable in it, but then specifying what the value of variable that you want to use. So I can scroll right and use y3. So that's the function with the variable that can change. And then I can set out that I want my value of a to be 3, for example, for y4, or for y5. I could say that I want my value of a to be equal to 4. Okay, so you don't have to enter functions with, for example, x squared subtract x subtract 3, or x squared subtract 3x subtract 3, or x squared subtract 4x subtract 3. You don't need to do that, because then if you have a different function, you would just change what y3 is. Okay, you wouldn't have to change lots of different functions. If you confirm then and then draw, you would get a series of curves that look like that. How could this help students? Well, they all appear to be going through the same y-intercept. Why is that happening? But it also appears that the vertex, shall we say, is moving to the right and down, perhaps. So is there a pattern going on? What particular pattern is there? Okay, and if you go back and link that to the algebra perhaps, or even the completed square format, there should be some sort of interesting revelations at this point. What you can do, this might be useful as well if you're going to draw lots of graphs, is that if you go to run matrix, let's just delete everything. You can actually enter a list of values if you want. If you use shift and multiply, that gives you the curly brackets, and then you can enter any values that you like. I'm just going to enter a few negative values, use a comma to separate, so that's just above blue delete key, close with shift and divide. And then what you want to do is that's actually a list of values, and then you can store it using the store arrow as a list. So if I now do shift, can you see that the list label is on the number 1? And then I can store it as list 1. There are 26 lists available. If you go to stats mode, okay, when you confirm with execute, list 1 in stats mode will now have these values in it. But quite nicely, you can also refer to them in graph mode. So what you could actually do is, let's delete Y5, and I can edit Y4. So let's just say that I still want my function Y4 to be something to do with Y3 that's got the variable in it. But this time I want the value of A to be the list that I just entered. So I only have to enter this once. So shift and 1 again, and then list 1. This time when you draw, you will get all those associated graphs. So you can see this time, when I've got A is now negative, it appears that the functions are now moving to the left and down, so the vertex. Okay, so interestingly, promoting all sorts of discussions about what's actually happening to your functions there. We can now have a look at templates. You can use built-in templates if you like. I am going to delete these functions. Okay. I'm only going to enter my quadratic and a built-in template. So if I scroll up to Y2 and then choose Tool and Built-in, you can see here there are built-ins available for linear. You've got completed square format and rectangular. You've also got a cubic and 3 trig functions that have got transformations as well. Okay. If we choose the completed square with select, that's F1, you can see that we have 3 variables that we can change now, A, B, and C. So now we can compare directly between our quadratic and completed square format. So if we draw, what you get there is, remember that A has the value of 1. B and C are both 0. We haven't changed those, and if you've got, remember to reset the handset, the default is 0. So they are not in the equation at the moment. So how would students interpret this? Well, obviously, if A is 1, that's 1 times the parentheses. If it was 0, you would get a flat line. Okay, so then what would you do further? Well, you could ask them, how can you get the red graph to become the blue graph? Something needs to happen. It looks like it needs to move horizontally and vertically. I don't think there's a vertical stretch going on there, or even a horizontal one. But can you now think that your students would use the coefficients, not coefficients, the variables B and C to adjust? You could do that by assigning them values in run matrix. Okay, or you could use modify. Okay, now modify, it's a really powerful function. I think it is brilliant when dealing with transformations. If you exit, you can see that modify is available instead of draw. So if you choose modify, what you get there is this screen where you can adjust the values of A, B, and C. You can do it by scrolling, or you can do it by directly entering values. The conclusions that students may come to is, what does A do? So the coefficient of your square parentheses, or B, which is the value inside the parentheses, and the C at the end. If they have a go at changing all of these values, they should be able to come up with something along the lines of, oh, A is a vertical stretch, B is a translation horizontally, C is a vertical. Okay, so doing their own investigations will allow them to come up with some conclusions. They may be incorrect, they may need a little bit of scaffolding, shall we say, but at least it allows them to see visually right in front of them what can be done. You may want to investigate the graphs. You can change the B or C, that is perfectly okay. But what we are going to do is I'm going to exit and I'm going to enter a value of 4 here. And the question that I may have is, why choose x equals 4? Sorry, y equals 4. Horizontal line, what's going on? I may be interested in investigating, one function compared to another, perhaps with some intersections. If I go at modifying, what we have here is we've got a equals 1. Let's change the value of b. So to do that, I can scroll down and then I just enter a value. Okay. If I do that, can you see that what we've got there is that appears slightly differently. Why is that different? Hang on a second. That's because I'm comparing it to x squared. Silly me. There you go. So now what we're doing is, there you go. That makes much more sense. There you go. I'm comparing an original function, say x squared, with completed square format. Okay. If b is 1, there is a suggestion perhaps that this is a horizontal translation. Okay. Again, helping students to realize which direction this is happening. If you exit, okay, away from modify, you're actually in draw mode. You can't analyze whilst you're in modify mode, so you do need to exit, and then we can shift and G-solve so that we can find some intersections. So because we have 3 functions drawn, need to choose which 2 that you want to analyze. So we've got our original x squared. Select that with execute. We don't want to find the intersection with our other quadratic, so let's scroll down and you can see the horizontal line is now flashing. So we've got 1 point of intersection there. If I scroll across, you can see that x equals 2, y equals 4. If you want to label that point, just press execute and you can see you get the coordinates 2, 4. If I do a little bit more analysis, so shift and G-solve, intersection between the other quadratic and our horizontal line. So let's scroll down to highlight that one. So that's the completed square format. And that is my horizontal line. You can see that you get that intersection on the left. If I scroll to the right and then choose execute, I get 3, 4. So you can see that the y value is the same, but the x value is increased by 1. And then you can make the very nice link between the translation and the particular coordinates. And you can do that for any point on these 2 functions. Okay. Other way of approaching this is you can use trace, for example. If I exit and get rid of my horizontal line, okay, this time if I modify and I set my value of b to 0, so I'm not moving it side to side, but then if I change the value of c, which is my constant, let's say -2 in this case, you will get that graph. If you then exit to draw mode and then choose trace, you can pick any points on the functions that you like. I'm just going to scroll across, or maybe just directly enter 2.4. Okay, so 2.4, x is 2.4, I get 5.76. Coordinates of values given at the bottom of the screen. I can label that with execute. But quite nicely, you can toggle between the functions when using trace. So if I scroll down, you can see that actually when x equals 2.4, I get 3.76. So again, making the link between the value of the variable c and the difference between the y values on our functions for the same value of x. Okay. Just to demonstrate, this is an exam question from 2022. Okay. This is dealing with a transformed sine function, but it's also the modulus of it. Okay, so please be aware that you can apply this to trig functions as well, and I'll show you that in a second. But also, it's really good for dealing with modulus questions. You can sketch those quite easily and find intersections. Here, we have some information that is required. So we've got maximum height of 50. It starts at 1 meter and it takes 720 seconds. Okay, so some of the things that may challenge your students when approaching this question, and if you do actually read the examiner's report on this question, it was not done very well. Which I find surprising, because trig transformations are quite nice, fairly easy to understand, and the calculator does make this quite an easy task. So how would students interpret this question? One of the things they may get wrong is it is in degrees and it is modulus. The modulus is important. Okay. They may not be 100% sure what the question's actually asking them. The problems they could face, obviously, understanding and guessing the correct transformations that are happening. What is A doing? What is B doing? What is alpha doing? And of course, this allows you, when teaching for a question like this, to vary the type of approaches that you may want to use. You know, is it purely, shall we say, numerical? Is it purely graphical? I would suggest as many different approaches as you can. It's best to visualize this sort of problem, I think. It's very nice of them that they do give you a little graph in the question, and that if students are paying attention, they can see there's a little bit at the end and the y-intercept is not 0. So they do need to pay attention there. Perhaps it might be useful to approach it this way. So if I delete all of this, you can use the built-in tool if you like. So I'm going to scroll down to sine. Okay. You can't directly use the modulus of the built-in tool, but you could enter the modulus of a manually entered transformation. The reason that I am going to enter it this way is because I quite like having both curves on there, because it does show the difference between the function and its modulus. To enter modulus, it's option and numeric, and then the absolute value. And I want the absolute value of my function y1. Okay. Or you could have just entered it as a modulus of a sine bx plus c. When you choose draw, what you'll get is a graph that is fairly unrecognizable, because you do need some suitable scales. So that is shift and view window, and there is a preset available, and that is trig. If you exit and draw, you get something that looks like that. And why is that? That's because we are in radians. Okay. This is one of the best ways that students are caught out, not realizing that the calculator by default is in radians. The question is in degrees. So let's choose setup. So that's shift and menu. And then let's change to degrees. When we exit and draw now, the graph still looks pretty bad because of our scales. So we're only going from -7 degrees to 7 degrees. So I need to use Shift View Window and use the trig preset again. Oh, hang on. Oh, I know. That's because it's, sorry, my bad. What is happening is that the values are 0. So actually I need to modify. B can't be 0. So let's have 1. There you go. So that makes a lot more sense. Okay. If I exit, I get the drawn value. And quite nicely, you can see you've got the original function, and the modulus shows that it's always positive, so that there are going to be regions that are relevant to this question. The question itself is going up to 720. Obviously, t cannot be negative, so I'm not particularly interested in the negative values. So what I can do is Shift View Window, and very nicely there is the facility where you can store settings, and this is vmem. You can store and recall these settings, so I think I've entered them as vmem2, possibly not, might have been vmem1. There are 6 settings available. No, didn't save them. So what I need to do is change these manually. Let's go, was it -20, 740, something like that. So the maximum was 720. Let's go up in 90s, and let's say that I want to go, I was told that the maximum, oops, sorry, yeah, right, let's do -60 and 60. So the maximum we were told was 60. Let's go up in 25s. Okay. If I exit and then draw, what we've got there is a very flat curve. That's because I've increased the vertical scale. If I want to get it to look like this, I need to modify it and say that I need a vertical stretch scale factor 50. Okay. So that is where you realize directly that the maximum value comes from the value of A. Oh, actually, I want C to be 0, don't I? There you go. Let's start off with that. Okay. So if you then exit and draw, that is what you're getting. However, if you want to extend this to the rest of the function, what you can do is realize that if I'm going from 0 to 720, that is a scale factor of 4, so that my value of A in this case, sorry, not A, B, get it right, needs to be 0.25. Okay, I don't know whether you can see on your handsets or on the emulator, but there is in fact a yellow ghost image, so you can see what the changes have occurred. So that makes a lot more sense now, because we're going from 0 to 720, because we're told that it takes 720 seconds to do a complete revolution for our Ferris wheel. If we then extend this just a little bit further, we know that when x equals 0, our height equals 1. So the equation is 1 equals 50 sine 0, sine alpha in this case. So you can solve if you want, or you could do a shift of a 50th. So inverse trig function, so you're solving an equation here. It is in degrees, okay? And just to make life slightly easy for yourself, what you can do is you can store the answer, so that's shift and negative, as the variable c, okay? So that is the last thing in your modified function. Okay, so that's nice and exact now. If you go back to a graph and modify, you will see that the value of C has been carried forward. Okay, and at this point, if you exit and analyze, you can in fact confirm that your graph is now correct. So for example, you could find the y-intercept of my modulus function. You can see y equals 1 when x equals 0. You could also analyze and find the maximum value of your modulus. Okay, y equals 50. We're not asked when it occurs, we just want to confirm that it does happen at 50. And you can also, if you want to do choosing further menu, you can do a ycal or an xcal. Let's do that one. Let's choose that and then say, what's the value of x? Well, that's 720. Oh, look, it is 1 high again. Okay, so that's confirming that all of your values are correct. So a very nice way to approach a question like that. It does help students out on their way to learning what is happening. Just briefly, sorry for overrunning, I only take 2 more minutes. Just a breakdown of how useful the handset is. What we've got there is students can do their own investigations, but just to demonstrate, it's really good for numerical integration and finding areas. So the difference between the integrals and the areas can be shown quite nicely. Really good for simultaneous equations. So you can see solve n here is finding the intersection between a circle and a line. Or you could have graphed y squareds, for example, to find out the values of x for the intersections. I personally think this is really good for modulus. So students sometimes get lost in the algebra and find erroneous solutions. So graphing these can demonstrate why they are erroneous. Parametrically, you can sketch functions and perform some calculus operations on there or find equations of tangents. You've got 3D lines, so intersections and relationships can be found. Probability distributions, this is excellent for discrete distributions now, especially right-hand binomial probabilities. It finds them really easily. Excellent for finding critical values, critical regions. SUVATs can be approached quite nicely using Solver, and you can also do numerical calculus using graph notation or even just graph it.